In this video, we will discuss the applications of the second derivative. The second derivative can be used to locate relative extrema. That means relative max or relative min. The second derivative can also be used to discuss the concavity of the original function. We can tell on what intervals a function will be concave up or concave down. We can also use the second derivative to identify points of inflection. That's where the function changes concavity. Either it goes from concave up to concave down, or vice versa. I need you to be emotionally prepared. These next couple of problems involve a lot of algebra. I did that on purpose. A lot of times I find that students don't actually have that much trouble with the calculus part of the problem, but then they mess up on the algebra. So these next couple of problems will give us a chance to practice and improve our algebra skills. Problem number 1. Given f prime of x equals 3x times x minus 2 squared times 3x plus 4, find the x value of any relative extrema. Justify using the second derivative test. First, we need to find the values of x that will cause f prime to equal 0. Since I gave you f prime in factored form, we can easily glance at it and see that f prime will equal 0 when x is equal to 0. That's from the first factor. When x is equal to 2 from the middle factor, and when x is equal to negative 4 over 3. Since we have been asked to justify using the second derivative test, we are going to have to find the second derivative. But I notice that we have three factors here, three functions of x. So we are going to use the product rule, but actually the extended product rule because we have three factors. So I'm going to go through this 3 times, and each time I will take the derivative of a different factor. The first time through, I take the derivative of 3x, which is 3. I leave the other two factors alone. So I still have x minus 2 squared, and I leave the 3x plus 4 the way it is. And I put a plus. Second time through, I'm going to take the derivative of the x minus 2 squared, but the 3x will be left alone. The derivative of x minus 2 squared is 2 times x minus 2. And I leave the 3x plus 4 alone. And I put a plus. The third time through, I leave the first two factors alone. So I have 3x times x minus 2 squared. But I multiply by the derivative of the third factor, which is 3. I simplified a little bit by multiplying 3x times 2, and I got the 6x, and I multiplied this 3 times the 3x to make 9x. But here's where that algebra comes in. We need to factor this, and we start by looking for a common factor. So as I scan through, I see that each of these 3 terms has a 3 in it. They're all divisible by 3. So I am definitely going to factor out a 3. Now, what about these parentheses? What do all of the terms have in common? They all have an x minus 2. So I am going to pull out x minus 2 as part of the GCF. So there it is. My GCF is 3 times x minus 2. I am going to put a bracket because some of the stuff that's left behind will have parentheses in it. So let's divide each of these 3 terms by 3 times x minus 2. If I divide the first term by 3 times x minus 2, the 3's will cancel out, and one of the x minus 2's will cancel out. But I will still be left with the other x minus 2, and the 3x plus 4 is still there. So that's the first term. If I divide the second term by 3 times x minus 2, 3 goes into 6 twice, so I'll have 2x remaining, and the x minus 2's will cancel out. So I have 2x times 3x plus 4. If I divide this last term by 3 times x minus 2, 9 divided by 3 is 3. The x remains. One of the x minus 2's will cancel out, but there will still be one left. So this is what I have inside of my brackets. On the next step, I'm going to get rid of all of the parentheses. So let's see. I am mentally multiplying these two binomials together. So I have x times 3x, that will be 3x squared. Inner, I have negative 6x. Outer, I have positive 4. Negative 6 and positive 4 make negative 2x. And then I have negative 2 times 4, which is negative 8. So this trinomial is the result of multiplying these two binomials. Now I will distribute the 2x across this binomial. So that will give me plus 6x squared plus 8x. Now I distribute the 3x across this binomial, and I get 3x squared minus 6x. I'm now looking for like terms to combine. If we combine these three terms that involve x squared, we get 12x squared. These x terms actually cancel each other out completely. Negative 2x plus 8x is positive 6x, and then 6x minus 6x is 0. So those are gone, and we are just left with the minus 8. I noticed that the 12x squared minus 8 has a common factor. These are both divisible by 4. So let's factor out a 4, and that 4 will end up multiplying by this 3 and make a 12. It makes a 12. So I have f double prime of x is equal to 12 times x minus 2. All right, I'm taking out a 4. So that will leave behind 3x squared minus 2. So you see what I meant when I said this problem has a lot of algebra in it. But, you know, it be like that sometimes. So now it's time to use the second derivative test to decide whether there is a relative max, a relative min, or neither at each one of these critical numbers. So the idea is we will plug these numbers into the second derivative, and we're looking to see if it is negative or positive. Is it less than 0 or is it greater than 0? So let's start with x equals 0. Let's plug that in. So I need to find f double prime at 0. So that would be 12 times 0 minus 2 times 3 times 0 squared minus 2. The 0 makes this term go away, and we can ignore that 0. So we just end up with 12 times negative 2 times negative 2. And all we care about is that this is positive. It is greater than 0. So this actually tells me that the original function must be concave up, but that means that any horizontal tangent line is going to be a relative minimum. So we just figured out that we have a relative minimum at x equals 0. Let's go ahead and write that up. I like to say f of x has a relative min at x equals 0 because blank and blank. Because I need to emphasize to you guys that the second derivative test always has two parts to it. The first part never changes. The first part says that f prime equals 0. And if you can remember to do it, it's best if you go ahead and put the value in here and say f prime at 0 is equal to 0, but f prime equals 0. The second part is where the second derivative comes in. So we found that f double prime at 0 was positive. So there is your second derivative test. We will do the same thing for the next value, x equals 2. So here I am plugging 2 into the second derivative. But notice that I have this 2 minus 2 right here. That's 0. So that's going to make this entire value equal to 0. And here's the thing. That is a fail for the second derivative test. The second derivative test doesn't tell us anything about whether there is a relative max or a relative min at x equals 2 when the second derivative is 0. It only works out when the second derivative is either positive or negative. So normally that would mean that we would need to go back and do the first derivative test to see what's going on at 2. But for this problem, the directions specifically said to use the second derivative test. And usually if this were a quiz or something, I might say, or say why the second derivative test fails. So this is what I'm going to do with this value this time. So the second derivative test fails at x equals 2 because f double prime at 2 equals 0. So I just want to emphasize to you that this does not mean that there is not a max or a min at x equals 2. When the second derivative test fails, we know nothing about whether there is a max or a min or neither at x equals 2. It just tells us that we would need to use the first derivative test if we really wanted to find out the answer. Now let's test out the third value, x equals negative 4 over 3. So here I have plugged negative 4 over 3 into f double prime, right where the x goes. So I'm getting this. I don't actually need to simplify this. All I care about is what the signs are. So notice that we have this 12, which is positive. And then we have a negative number, and then we're subtracting, so that's going to be a negative. If you take negative 4 over 3 and square it, that's going to be a positive number, right? That would be 16 over 9 once we squared it. Anyway, that's being multiplied by 3, so that's definitely bigger than 2. So when you subtract 2, it will definitely be a positive number. So when you have a positive times a negative times a positive, that is a negative. So this is less than 0. So remember, because the second derivative is negative, that really means that the function is concave down in this area, which means that a horizontal tangent line will be at a relative maximum. Let's write it up. One more time, remember that the second derivative test requires two parts in the justification. We say f of x has a relative max at x equals negative 4 over 3 because f prime at negative 4 over 3 is equal to 0. That's the first part. And f double prime at negative 4 over 3 is negative. Make sure when you do the second derivative test, you include both of these parts. Notice that problem number 2 involves the same function as above, so we will not have to do that work over again, thank goodness. Given that f prime is equal to 3x times x minus 2 squared times 3x plus 4, find the x value of any points of inflection. Justify your answer. Let's copy down the f double prime that we found in problem number 1. Here is your second derivative. But here's the key. A point of inflection occurs when f double prime changes signs. For that reason, we need to make a sign chart so we can analyze where the sign changes. In order to make a sign chart, we need to record the values of x that will cause f double prime to equal 0. So let's see, where will f double prime equal 0? In factored form like this, it's easy to see that f double prime will equal 0 at x equals 2. And, well, okay, this one might take a little bit of extra thought. Maybe I'll do it off to the side. We have 3x squared minus 2 is equal to 0. Adding 2 and dividing by 3, we get x squared is equal to 2/3. But then we have to take the square root of both sides. So that is going to give us x is equal to plus or minus the square root of 2/3. All right, so we have 3 values to put on the number line to make the sign chart. Here are the 3 values on my number line in order. Make sure you label the sign chart as f double prime. We will need 2 rows, one for each of these factors. I am not including the 12 on here because it is a positive constant, so it is not needed. If this was a negative 12, I would put it on the sign chart because that would put a bunch of negatives all across, which would change the answers to the opposite of what they would be. But if let's say I did this whole sign chart and I had all of my answers finished. If I went back and said, oh no, I forgot the 12, and put a bunch of positives on the 3rd row, would that change anything? No. So the positive 12 doesn't matter. That's why I leave it off. Anyways, we need to decide whether these factors are positive or negative in each interval. The x minus 2 factor gave me the 0 of 2. So this is sort of the cutoff right here. And I know that x minus 2 will be negative to the left of 2, and it will be positive to the right of 2. The 3x squared minus 2 gave us these radicals. So these are the places where this might change. So I'm just going to focus on that. So we just need to worry about inside of here and outside of here, really. So let's start with between negative and positive radical 2 over 3. These are pretty close together, but I don't care because I definitely want to use 0 for my test value, right in the middle. And if I plug in 0, then this term goes away. I'm left with negative 2, so I know this is going to be negative. Okay, if I pick a value that's bigger than this, okay, like 2/3, the square root of 2/3, this is less than 1. So I could just pick the number 1, for example. So let's say if I put in a value of positive 1. 1 squared is 1, that just leaves 3. 3 minus 2 is 1, that's positive. Okay, that means it's all positive over here from now on. What about to the left? Well, what if I pick negative 1? It would be the same answer because negative 1 squared becomes a positive 1. I still have 3 minus 2. That is still positive. So, what about the overall sign of f double prime in each interval? In the first interval, I have a negative times a positive, so that's a negative. A negative times a negative is a positive. A negative times a positive is a negative. And a positive times a positive is a positive. So remember, a point of inflection occurs when f double prime changes signs. So each of these 3 values represents the location of a point of inflection because f double prime changes signs again, and changes signs again. Let's write it up. We say f of x has a point of inflection at x equals 2 and x equals plus or minus the square root of 2/3 because f double prime changes signs at these values. One more. Given g prime of x equals 5 times 3x minus 2 to the negative 1/3 power, discuss the concavity of g of x. Justify your answer. Well, concavity depends on g double prime. So we need to find the second derivative. So let's do the chain rule. We need to take the negative 1/3 and multiply it by 5. So that will give us negative 5/3. times 3x minus 2, subtracting 1 from this exponent, so I'm thinking minus 3 over 3, so that'll be negative 4 over 3. And don't forget the chain rule, so we need to multiply by the derivative of the inside. So that's going to be times 3. Notice that these 3's will cancel each other out. So we end up with g double prime is equal to negative 5 times 3x minus 2 to the negative 4 over 3 power. In order to discuss the concavity, we are going to need a sign chart of g double prime. To make the sign chart, it will be slightly easier if we go ahead and write this as a fraction. So we have g double prime is equal to negative 5 over 3x minus 2 to the 4/3 power. To make the sign chart, we need to know where g double prime is equal to 0 and where g double prime is undefined. But in order to set a fraction equal to 0, you actually set the numerator equal to 0, but the numerator is a constant. Negative 5 can't equal 0, so we have no solution to that part. So let's move on to where is g double prime undefined. So we can just look at this and see that g double prime will be undefined when the denominator is equal to 0. If I set this equal to 0, you know what, I think I better do this. I started to just write the answer, which is x is equal to 2/3. But I'm remembering that some students didn't necessarily know that automatically. So here's what I'm doing. I am setting 3x minus 2 to the 4/3 power equal to 0. So technically, in order to solve this, I need to get rid of this exponent. And the most efficient way to do that is to raise both sides of the equation to the reciprocal power. So I'm going to raise the left and the right side of the equation to the 3/4 power. When you raise a power to a power, you multiply. So these will cancel each other out. That's why I did it. So those exponents are gone now. So I am left with just 3x minus 2. And of course, 0 to whatever power is still going to be 0. And the rest, I'm sure you can do in your head. So I just added 2 divided by 3. That's where the 2/3 came from. So in the future, you can see that if I have some factor with an exponent and I'm setting it equal to 0, no matter what the exponent is, it's going to cancel out. So I can just skip to setting the inner part equal to 0, which you can almost always do mentally. So we have this. Time for the sign chart. So this will be the only value on the sign chart. So here's my sign chart. Make sure you label it as g double prime. I put a little arrow to show that this is where 2/3 is. And I'm going to have 2 rows on my sign chart. I need a row for the constant and a row for the denominator. On a previous problem, I did not include the constant, but that's because it was a positive 12, I think it was. If it's a positive number, you don't need it. But if it's a negative number, you do need it, because negative values, see where this negative 5 is? I'm going to put negatives all across here. That will change everything to the opposite sign of what it would be if I didn't have this row. So please do not leave off the negative 5. The negative 5 matters because it is negative. So the other thing that is very important, a lot of students will look at this and start thinking about where 3x minus 2 is negative and positive, and then that's what they put on the chart. But that is wrong, because when you have a fractional exponent, it is in the form power over root. So what I really have here is the 4th power. So this entire thing is being raised to the 4th power. You know how when you square something, you know it's automatically going to be positive. Well, that's true for any even power. So because we are raising something to the fourth power, this is going to be positive no matter what. So we don't have to think about it or plug in test values. It's automatically positive. If this had been, I don't know, a 5, if this had been 5 over 3, then we would have like a negative and a positive and things would change. All right, even power, everything's positive. So we have a negative divided by a positive, which is a negative. And same thing in the next interval, so this is also a negative. We are to discuss the concavity. And we know that if g double prime is negative, that means that the original function g of x is concave down in that interval. If these had been positive, g of x would be concave up. So let's write it up. We say that g of x is concave down on the intervals from negative infinity to 2/3, union 2/3 to infinity, because g double prime is less than 0. Notice that I did not say concave down from negative infinity to positive infinity. I purposefully skipped over the value of x equals 2/3. That's because g double prime is undefined right there. So that is not to be included in this interval. Even if g double prime were equal to 0 here instead of undefined, when it's equal to 0, it's not negative. So that means it's technically not concave down when g double prime is equal to 0. So either way, I'm going to leave out this, this value where it's right on the line. So that was a nice little review of the applications of the second derivative. To summarize, we can use the second derivative to locate and identify relative max and relative min. It's called the second derivative test, and we take our values where f prime equals 0, and we plug those into the second derivative, and we see if we get a positive or a negative. If we get a positive, that actually means the function is concave up, so that means you have a relative min. If you get a negative, the function is concave down, so that is a max. Make sure when you justify that your second derivative has two parts to it. F prime equals 0, and f double prime is either negative or positive. The other thing we are able to do is we can locate a point of inflection using the second derivative. A point of inflection occurs when f double prime changes signs. So we have to make a sign chart and just see where it changes signs, and that'll be a point of inflection. And finally, we can use the second derivative to discuss the concavity of a graph. And again, we just make a sign chart, and wherever the second derivative is negative, the original function f of x or g of x will be concave down. Wherever the second derivative is positive, it will be concave up.